Welcome to the Sleepy Professor. Tonight we're going to drift into one of the most fascinating mysteries of the universe, the speed of light. We'll unravel its secrets, explore why it moves the way it does, and discover how this single constant rhythm shapes everything from the ticking of our clocks to the way we see the stars. So settle in, let your mind wander, and let's journey together through the quiet elegance of light's timeless pace. Have you ever wondered why light, the fastest thing in the universe, doesn't just go faster? It zips across the cosmos, paints our skies with sunsets, carries the stories of distant stars into our eyes. And yet it has a hard limit, a cap, a cosmic speed sign that says, this far, no faster. It's not just fast, it's defined, fixed, unbreakable. But why? Why does light of all things, a thing with no mass, no rest, no baggage, obey such a strict rule? Tonight, we'll ease into that mystery together, not with frantic equations or complicated diagrams, but with curiosity, calm, and wonder. Wherever you are right now, lying in bed with your head just sinking into the pillow, curled up in a corner of your sofa, or maybe just staring softly at the ceiling while your thoughts drift, you've made your way to a little corner of quiet exploration. This space isn't for cramming facts or stressing over answers. It's for slow thinking, for letting your mind wander gently through strange ideas that somehow make the world feel more grounded. Science has this wonderful power, not to overwhelm us with how much we don't know, but to comfort us with how beautifully everything fits together when we look closely. And tonight, we're looking at light, that familiar, glowing friend that helps us read, see, cook, find our keys, admire the moon, and maybe even feel a little safer in the dark. But beneath that everyday brightness, light carries one of the most profound secrets in all of physics. It seems almost silly at first. Of all the questions you could ask about the universe, why are we here? What is time? What happens inside a black hole? Asking why light has a speed limit might feel like asking why water gets wet. It just is, right? We know the number. It's fast. End of story. But in truth, asking why light travels at the speed it does is like tugging a single thread and watching the entire fabric of reality shift. Because that speed is more than a measurement. It's a constant in equations that govern everything, from the rhythm of your heartbeat to the curve of galaxies. It defines what's possible and what's not, what can be known and when. It touches not just how light moves, but how time itself flows. So tonight, we won't rush. We'll let the question unfold slowly. We'll walk through the history, the physics, and the poetry of it. Because if you listen closely, this question doesn't just whisper about light. It tells us something about the nature of the universe itself, something about boundaries, about harmony, about the quiet order that makes reality work. And the best part? You don't need to understand every formula or memorize any facts. You just need to wonder, to let the question settle softly into your thoughts. Why can't light go faster? Why does the universe insist on that one speed? What would happen if it could be broken? Or if it had never existed at all? These aren't just bedtime musings. They're windows into how everything fits together, from stars and satellites to your morning coffee and the message traveling through your phone right now. So let's take that first quiet step. Not to race toward an answer, but to savor the question. Let's stretch out beneath the stars, tilt our heads toward the unknown, and follow a photon as it races through the vacuum. Not just to see how fast it moves, but to discover why it never moves any faster. The speed of light isn't just about motion, it's about meaning. And tonight, we begin to unwrap that mystery together, one thought at a time. When we say the word light, we usually mean the stuff we see with our eyes, the warm, golden sunlight spilling across your floor in the late afternoon, the glow of a reading lamp by your bed, the soft flicker of a candle. It's everywhere, so familiar, that it hardly feels mysterious. But the deeper you look, the stranger it gets. Because light isn't just something that helps us see. It isn't just brightness or glare or color. It's one of the most peculiar, profound phenomena in the universe. We think we understand it until we try to explain what it actually is. And then things start to get wonderfully strange. Light begins with something called a photon. That's the smallest possible unit of light, like a single note in an enormous cosmic symphony. But a photon isn't like a grain of sand or a droplet of water. You can't hold one. You can't weigh it. In fact, a photon has no mass at all. It doesn't rest, doesn't stop, doesn't age in the way we understand time. Once it's born, emitted from the sun, or a light bulb, or even the warmth of your own skin, it travels instantly at full speed, like it knows exactly where it's going. But calling it a particle only tells half the story, because light isn't just a particle, it's also a wave. Not a wave like you see in the ocean, with rolling crests and splashes. Light is an electromagnetic wave, which means it's made up of electric and magnetic fields, vibrating together. These two invisible forces ripple at right angles to each other, and also at right angles to the direction the light is moving. It's like a perfectly synchronized dance. Two partners swirling together through the emptiness of space, never touching, never out of step. And the most beautiful part? This wave doesn't need a medium. Sound needs air. Water waves need water. But light needs nothing. It travels through the vacuum, through the void, as easily as it travels through glass or air. It doesn't need to be carried. It is the carrier. This is why we can see stars. Their light has crossed millions or even billions of years of cold, empty space, uninterrupted. It doesn't fade. It doesn't pause. It just keeps moving, steady and sure. Imagine that. One tiny photon leaving the surface of a distant star before our planet even existed, traveling across unimaginable distances, only to gently strike your eye tonight. That's what you're seeing when you look at the stars. Not just brightness, not just beauty, but history carried by light. And yet, for all its elegance, light doesn't behave the way we expect particles to behave. It bends around corners. It interferes with itself. It can be reflected, refracted, scattered. Shine it through a tiny slit, and it creates patterns of light and dark bands, like a ripple in a pond. But those aren't just waves of energy. They're also probabilities. Because when we look closely, uncomfortably closely, we find that photons don't just go from one place to another in a straight line. They explore all possible paths. They might go this way or that way, or both at once, or take a strange looping route that makes no sense until you realize it does. That's the world of quantum physics, where light becomes something more than wave or particle. It becomes possibility. And yet, despite all this weirdness, it works. The light bouncing off your favorite book right now, entering your eyes, triggering cells in your retina, creating the sensation of color and shape and meaning. None of that would be possible if light weren't both a wave and a particle. If it didn't travel at exactly the speed it does. If it didn't follow the bizarre but consistent rules that make our reality tick. Light is the bridge between the quantum and the classical, between what we know and what we don't. It's the thread that connects atoms to galaxies, and somehow also the thread that connects you to everything you see. And yet, the more we try to define it, the more it slips through our fingers. We can say that it carries energy. We can measure its frequency, its wavelength, its polarization. We can split it into colors, or convert it into electricity, or trap it in a mirror and bounce it endlessly. But the moment we ask, what is light really? We find ourselves staring into one of the deepest mysteries in science. Not because we don't know anything about it, But because we know so much, and it still doesn't fit into any single box, it is energy and information. It is vibration and flow. It is quantum and wave and particle, and yet none of those alone. It is how we see, how we know, how we connect. And to even begin understanding why it has a speed limit, we first have to accept how strange it already is. Light is not a thing in the way most things are. It is a process, a pattern, a presence, always moving, never resting. The closest thing to pure motion the universe has ever made. It is both the question and the way we see the answer. And it's only just getting started. If you were to look at light with only your eyes, you might think it's simple. A soft white glow from a bulb, the colours of a sunset melting from orange to pink, the green of a leaf in the sunlight, the red of a stop sign, the soft blue of the sky on a clear day. These are all just parts of light that we can see, but they are only the tiniest slice of what light really is. Imagine a piano stretched across an entire football field. Now imagine that the handful of visible notes we play, red, orange, yellow, green, blue, indigo, violet, are just a few keys near the middle. That's all the light our eyes can detect. But the piano keeps going, far to the left and far to the right, in frequencies we'll never see, but which shape our world all the same. Light is much more than what we can perceive. It is a vast, invisible spectrum, full of surprises. To the left of that piano, where the keys grow deeper and slower, we find radio waves. These are the giants of the electromagnetic spectrum, long, stretched-out waves that can reach for miles or more. They bring us music, news, stories, weather reports. But more than that, they pass through buildings, bend around mountains, whisper across continents. They're not heard by our ears directly, but they're translated by antennas and radios into something meaningful. And they're still light. Not a different thing, not a cousin, just light, wearing a longer wavelength. Shift just slightly, and we reach microwaves. The same kind of waves that heat up leftovers in your kitchen also carry signals between cell towers and satellites. They can pass through clouds, through skin, through the atmosphere, and yet they're just another variation of light. Shorter than radio, faster, more focused, still invisible, still real. Slide a little further and you enter the infrared. This is the region of warmth, the light that your skin can feel, even if your eyes can't see it. Everything with heat emits infrared radiation. Your body, your dog, the earth itself glows in this soft thermal light. Night vision cameras can see it. Some animals can see it. It reveals a hidden world of temperature and energy just beyond human perception. Then finally, we step into the narrow band we call visible light, the only region the human eye is tuned to detect. Here the waves are just the right size to trigger the cone cells in your retina. Each color has a different wavelength, red with the longest, violet with the shortest. Our eyes interpret the frequency of these waves as color, but color itself isn't out there in the world. It's an experience, a sensation your brain creates from light's rhythm. The world isn't colored, the light is, and we respond to its vibration as if it were music. But don't stop at violet. Beyond the edge of what we can see lies ultraviolet, shorter, sharper, more energetic. This is the light that gives you sunburn. It can damage cells, alter DNA, but it also has uses. It disinfects, sterilizes, reveals hidden markings in flowers that insects can see, but we cannot. Ultraviolet is just beyond our reach, a reminder that seeing is not the same as knowing. Go shorter still, and the waves become X-rays. Powerful beams that pass through soft tissue and reveal the bones underneath. In hospitals and airports, we use them to peer into things we normally can't. They aren't magical. They're just high-energy photons, with the ability to cut through matter depending on how dense it is. And even then, light still obeys the rules. And finally, at the far end of the spectrum, we find gamma rays. These are the most energetic, most extreme forms of light. They emerge from the hearts of dying stars, from nuclear reactions, from the edges of black holes. They can pass through nearly anything. They carry the whispers of the universe's most violent events. You wouldn't want to meet them without a thick wall of lead between you and the source. But again, they're just light. Still photons, still following the same strange law that governs every other wavelength. So from the longest, slowest radio waves to the fastest, shortest gamma rays, what we call light spans a range so vast, it's almost impossible to comprehend. And yet, across this entire electromagnetic spectrum, something remarkable holds true. No matter how different these forms of light appear in behavior or energy, in a vacuum, they all move at the same exact speed. Whether it's a gentle FM radio wave curling through your kitchen, or a deadly gamma ray streaking through interstellar space, the velocity never changes. All light, when unimpeded, travels at that one perfect pace, about 299,792,458 meters per second. Not one faster, not one slower. It doesn't matter how much energy it carries. It doesn't matter how dangerous, how useful, how invisible or dazzling it is. If it's light, if it's part of this spectrum, it abides by the same rule. This unity across variety is one of the strangest and most beautiful truths in physics. It's like discovering that every kind of music, from whispers to roars, plays at the same tempo. A cosmic rhythm, silent to the ear, but pulsing through every corner of the universe. That sameness is not trivial. It suggests something deeper about the nature of light, that this limit is not imposed from the outside, but arises from light's very identity. It's not that someone set a speed limit for light. It's that light, in all its forms, is defined by how it moves. And to understand why it moves that way, and not faster, we have to go beyond what it is and begin to explore what it means. Because this spectrum isn't just a range of radiation. It's a language, a story, a code written across time and space, always traveling, always moving, always bound to the same gentle, unwavering speed. Let's talk about speed. Not the kind you feel in a car or on a roller coaster, but the kind that feels too big to hold in your head. The kind that travels across galaxies, crosses the emptiness of space without slowing down, and delivers ancient starlight directly to your eyes. The speed of light is not just fast, it's the fastest. It's a number so vast that it almost doesn't feel like a number at all. In a vacuum, where nothing gets in its way, light moves at 299,792,458 meters every single second. That's just under 300,000 kilometers per second. Not per hour, per second. It's so quick that even imagining it feels like trying to count to infinity. To give that some weight, imagine this. If you could travel at the speed of light, you could circle the entire Earth more than 7 times in 1 second. That's not metaphor or exaggeration. That's just the math. You could blink, and your light self would have already zipped around the planet before your eyelids had the chance to meet. And yet, as dizzying as that sounds, light speed is more than just a measurement of incredible motion. It's not like the top speed on a car or the record on a track. It's a fundamental property of our universe, a built-in, non-negotiable rule that everything, everywhere, must respect. Nothing with mass can ever reach it. No information can travel faster. It's not just fast, it's final. So where does this speed come from? It turns out, light isn't moving fast just because it wants to. It's moving fast because it has no choice. A photon, The tiny quantum of light has no mass and no rest. That means it can't slow down, but it also can't speed up. The moment a photon is created, whether it's from the burning core of a star, the flick of a candle flame, or the snap of a finger on a touchscreen, it's already moving at light speed. It doesn't accelerate, it doesn't wind up. It's born in motion, and it stays in motion until it's absorbed. There's no such thing as a photon at rest. If it were to stop, it wouldn't be light anymore. It would simply cease to exist. Now, it's tempting to ask why this particular number, 299,792,458 meters per second. Why not a nice round 300 million, or 500 million, or why not infinite? It seems almost arbitrary until you realize that this number is not random at all. It's built into the very fabric of the universe. Light speed is determined by the nature of electric and magnetic fields, the very forces that give rise to light in the first place. The vacuum of space isn't truly empty. It has properties, structure, constants. And when you plug those constants into the equations that describe how electric and magnetic fields interact, Maxwell's equations, you get this number. That's the speed the universe allows. That's the pace at which electromagnetic waves can ripple through space. It's not optional. It's not up for debate. It's a reflection of how space and time are stitched together. And while it may seem impossibly fast to us, the universe doesn't treat it that way. To the universe, light speed isn't fast. It's standard. It's the baseline, the unchanging reference that everything else is compared to. In fact, scientists no longer even measure the speed of light the way we used to. Since 1983, we've actually defined the length of a meter by how far light travels in a tiny fraction of a second. That's how fundamental this speed is. It's not something we measure anymore. It's something we use to measure everything else. Even more strange is that light doesn't always move at this speed. In a vacuum, yes, it moves at its full pace. But when it enters a material like water or glass, or even the lenses in your eyes, it slows down. Not because the photon is tired or sluggish, but because it's constantly interacting with the atoms in the material. It gets absorbed and re-emitted, scattered and delayed, bumped and bounced around. The net effect is that the light takes longer to get through. But between each of those interactions, it's still moving at full speed. It's just being rerouted over and over again, like a commuter weaving through a crowded train station. And that's why you get things like refraction, when a straw looks bent in a glass of water, or why a diamond sparkles. The path of the light bends, slows, and changes direction. But even when slowed down, light is still following the rules, still respecting the speed limit in every tiny segment of its journey. There's something oddly comforting about this consistency, that no matter the situation, no matter the wavelength, no matter how the light was created or where it's going, it always travels at the same fundamental speed, unless it's forced to slow down by matter in its way. It's like a runner who never tires, never stops, but occasionally has to dodge a few obstacles. And even then, the runner's pace never falters. It's just the route that becomes more complicated. So the next time you see a beam of sunlight pouring through a window or a flashlight cutting through the dark, remember that what you're seeing isn't just brightness. You're witnessing a law in motion, a rule that has never been broken, not once, in all the history of the universe. From the glow of your screen to the most distant galaxy, the photons all travel at the same speed, set by the structure of reality itself. And maybe, just maybe, that shared motion, that universal pace, is part of what makes light so beautiful. It's not just fast, it's perfect, it's precise, and it's never late. For most of human history, the idea that light might take time to travel from one place to another was almost unthinkable. It just didn't feel true. You lit a candle, and the room brightened. You opened your eyes at dawn, and the sunlight was already there. There was no waiting, no pause. Light seemed instant, like a switch flicked by the universe. The notion that something so fast could also be finite didn't occur to most people, not because they lacked intelligence, but because they had no reason to suspect otherwise. The world was full of immediate brightness. Light was there when it was needed. No hesitation, no delay. It simply appeared. The ancient Greeks, always curious, toyed with the idea. One philosopher named Empedocles was among the first to suggest that light might move at a finite speed. He imagined it traveling from object to eye, not arriving all at once, but with a slight invisible delay. But ideas like his were hard to test and harder still to prove. So they faded into the background. Aristotle, whose views dominated scientific thought for centuries, insisted that light traveled instantaneously, and that was that. In those days, if Aristotle said it, you didn't really argue. For a long time, the question lay dormant. People had more immediate mysteries to solve: why the stars moved the way they did, what fire really was, how to measure the earth. But then came the Renaissance, and with it, a new breed of thinker. People who weren't content to simply accept the way things seemed, but who wanted to measure, to observe, to challenge. One of these was Galileo Galilei. Galileo was not a man easily satisfied by assumptions. He was a tinkerer, a stargazer, a relentless questioner. Around the year 1638, he came up with a bold and simple experiment to measure the speed of light. The plan? He and an assistant would each take a covered lantern and stand on two distant hilltops about a mile apart. Galileo would uncover his lantern. As soon as his assistant saw the light, he would uncover his lantern in return. Galileo would then time how long it took for him to see that second light. It was an elegant idea, beautiful in its simplicity, clever in its design. But there was a problem. Light, as we now know, can travel a mile in just over 5 microseconds. That's 5 millionths of a second. Human reaction time, even in the best conditions, is hundreds of times slower than that. To Galileo, it seemed instantaneous. He concluded, with honesty and humility, that if light had a finite speed, it was too fast for him to measure. Still, the seed had been planted. The question had been asked out loud, not as a thought experiment, but as something that might be tested, measured, proven. And in science, asking the right question is often more important than having the right tools. The pursuit had begun. Nearly 40 years later, a Danish astronomer named Ole Rømer would take the next step, accidentally. In 1676, while studying the moons of Jupiter, Rømer noticed something strange. One of Jupiter's moons, Io, moved around the giant planet with clockwork precision. It disappeared and reappeared behind Jupiter on a regular schedule. But as Rømer tracked it over many months, he saw that its appearances weren't always on time. Sometimes Io was a little early, sometimes it was late. The timing shifted depending on the time of year. To some, this might have looked like a flaw in the moon's motion, but Rømer had a different idea. What if the moon wasn't the problem? What if the delay came from the light itself? When Earth was moving away from Jupiter in its orbit, the light from Io had farther to travel. And when Earth was moving toward it, the distance was shorter. That would explain the changing delays. By calculating the difference, Rømer estimated how long it took light to cross the Earth's orbit, a staggering distance, millions of miles wide. He estimated it took about 22 minutes. His number wasn't exact, but his conclusion was revolutionary. Light takes time. Not much, but enough to measure. It had a speed. It wasn't infinite. The cosmos, it turned out, didn't flick a switch. It sent a signal. And that signal took time to arrive. This was the first solid evidence that light wasn't instantaneous. It had a pace, and that pace could be tracked. Rømer's discovery changed how we saw light. not just as something bright or useful, but as something physical, something with motion, something we could study like any other natural phenomenon. For the first time, light wasn't just presence, it was a traveler. More scientists followed, refining the measurements. In the mid-1800s, Hippolyte Fizeau built an ingenious setup using a rotating toothed wheel and a mirror placed several miles away. A beam of light passed through one of the gaps in the wheel, bounced off the distant mirror, and came back. If the wheel spun slowly, the light returned through the same gap, but if it spun fast enough, the returning beam would hit a tooth instead and be blocked. By adjusting the speed of the wheel and measuring the distance, Fizeau could determine exactly how long the round trip took, and thus how fast the light had traveled. His answer: around 313,000 kilometers per second. Not perfect, but astonishingly close, given the era. A few years later, Léon Foucault improved the experiment, using rotating mirrors instead of wheels, and brought the estimate even closer to the modern value. He also proved that light travels more slowly in water than in air, showing that its speed could change depending on the medium. That might not sound dramatic now, but at the time, it was huge. It meant that light interacts with matter. It bends, it slows, it responds to its surroundings. It is not untouchable, it is real. The story didn't end there. In the late 19th century, Albert Michelson, who would later become the first American to win a Nobel Prize in science, took up the challenge. Using more refined tools, longer distances, and greater precision, Michelson measured the speed of light again and again, each time honing the number. His work became the gold standard, and his legacy shaped modern physics. Today, we don't just know the speed of light, we define our units of measurement by it. But none of this would have happened if someone hadn't first stopped and asked a simple question: does light take time? And that question, once whispered in a world of candles and stars, rippled forward through generations. It passed through the minds of philosophers, astronomers, inventors, and dreamers. It turned into experiments. It shaped our understanding of space, time, and the structure of the universe. So the next time you flick on a light and the room brightens, remember this: what feels instant is not. That glow you see is the final step in a journey that's been measured, calculated, chased across centuries. Light has a speed, it has a story. And the moment humanity dared to measure it, the universe began to reveal just how carefully, how beautifully it keeps its time. Once the truth about light's speed began to take hold, the questions only deepened. Measuring that speed with increasing precision was no longer just a scientific curiosity. It became a quest to understand something far more profound. Because if light had a speed, and if that speed was constant, then what did that say about space itself, about time, about the very structure of the universe? The 19th and early 20th centuries became an era of refinement, of tools growing sharper, of theories turning from guesswork into laws. Light was no longer just an everyday glow. It had become a ruler, a guide, a key. And humanity, ever persistent, set out to chase it with every ounce of cleverness it could summon. Albert Michelson, whose name still echoes through physics textbooks, played a central role in this pursuit. His goal was simple but daunting: measure the speed of light as accurately as possible. Over the course of years, he developed methods using rotating mirrors and vast tunnels, bouncing beams of light across great distances, and timing their return with exquisite care. His experiments didn't just improve earlier measurements, they set a new standard. Michelson's results were so precise that they became a reference point for other sciences. He wasn't just studying light, he was redefining how we study anything at all. And his legacy didn't stop there. His techniques laid the foundation for one of the most famous experiments in history, the Michelson-Morley experiment, which would go on to shake physics at its roots. At the time, many scientists believed that light, like sound or water waves, needed something to travel through, a medium they called the ether. This ether, they thought, filled all of space invisibly, silently, allowing light to ripple through it. But if the Earth moved through this ether, then light's speed should change depending on whether it was moving with or against this invisible current, just like a swimmer going with or against the flow of a river. Michelson and his colleague Edward Morley designed an experiment to detect that change. They expected to find slight variations in light speed, depending on the direction it traveled. What they found instead was nothing. No difference. No ether. The speed of light, it turned out, was the same in every direction, at every time, no matter what. This result was baffling. It didn't fit the current models. If light needed no medium, and if it moved the same way regardless of the observer's motion, then something was wrong. Not with the data, but with the very assumptions scientists had been using to describe the universe. And that is when everything began to shift, because that strange, stubborn constancy of light speed became the cornerstone for something new, something revolutionary. Enter Albert Einstein. In 1905, a quiet patent clerk with a mind full of thought experiments proposed a radical idea. What if the speed of light wasn't just a feature of light, but a foundation of reality? What if this speed was the same for all observers, no matter how fast they were moving? And what if, to preserve this universal speed, space and time themselves had to bend? Einstein's special theory of relativity took the constancy of light speed and turned it into the bedrock of a new physics. No longer was space a fixed stage where events happened. No longer was time an unchanging rhythm ticking evenly throughout the cosmos. Instead, space and time were fluid, interwoven, responsive to motion and mass. Moving clocks would tick slower. Moving objects would shrink in the direction of travel. Events that seemed simultaneous to one person might not be to another. It was as if reality itself bowed to protect the one thing it could never compromise: the speed of light. And suddenly, Michelson's careful measurements were no longer just numbers. They were prophecies. His relentless pursuit of precision had pointed the way toward a deeper truth. Light wasn't just fast, it was a constant, an anchor, and the universe was built around it. From that point forward, the speed of light wasn't simply a thing to be measured. It became the foundation for how we define measurement itself. In 1983, the scientific community made a bold decision. Rather than continuing to chase ever more precise measurements of light speed, they flipped the script. They defined the meter, our standard unit of length, based on how far light travels in a tiny fraction of a second. Specifically, 1 meter is now the distance light travels in 1,299,792,458 of a second. In doing so, we didn't just standardize a number, we acknowledged something far more poetic: that this speed is so dependable, so universal, that it could serve as the very fabric from which we measure space and, indirectly, time itself. Think about what that means. Every ruler you've ever used, every distance you've ever measured, every GPS signal that's ever guided your path, all of them are quietly relying on light's unwavering pace. It's not just a speed in space, it's the rhythm of the cosmos. It's the metronome that underlies everything from the flutter of an electron to the spin of a galaxy. Even the tools we now use to keep time, atomic clocks, depend on electromagnetic radiation and its behavior. Without light's constancy, we wouldn't know where we are, when we are, or even how fast we're moving. And yet, for all its precision, there's something deeply human in this journey. From lanterns on distant hills to beams bouncing off mirrors, from watching the moons of Jupiter to spinning intricate wheels with polished gears, every step has been marked by a kind of quiet determination, a willingness to look closer, to think harder, to ask not just what the universe does, but why it does it that way. And it's no coincidence that the one thing we tried to catch, light itself, turned out to be the very thing that shows us how to measure the world. So now, when you see a street lamp flicker on, or sunlight glint off a puddle, or starlight shimmer in the night sky, you're not just seeing illumination, you're seeing a principle etched into reality, confirmed by centuries of effort, and still guiding the way we understand existence. The speed of light isn't just how fast light goes, it's the pace at which reality allows anything to happen. It's the ultimate limit, the golden thread that binds space and time together. And it's still there, in every reflection, every spark, every shadow, waiting to be seen, waiting to remind us just how far we've come to understand even a sliver of what it really means. The deeper we peer into the nature of light, the clearer it becomes that its speed is not just fast, it is fundamental. And yet, for all our measurements, all our definitions, one haunting question still lingers like a distant echo. Why? Why that speed, specifically? Why can't light go just a little bit faster, or infinitely fast, or behave like the objects in our everyday world, where speed is flexible, where acceleration is a choice, where a little more force means a little more motion? In our daily lives, speed is something we can control. Push harder, go faster. But light doesn't play by those rules. It doesn't accelerate. It doesn't rest. It doesn't even hesitate. It always moves at the exact same speed, with no variation, no exceptions, no room for negotiation. And that strange, stubborn consistency leads us into one of the most elegant and mind-altering regions of modern physics. To find out why light has this unyielding limit, we need to leave behind the comforting rhythms of common sense and wander into the invisible forces that govern the universe itself, into the dance of electricity and magnetism. In the mid-1800s, a Scottish physicist named James Clerk Maxwell took everything scientists knew about electric charges and magnetic fields and brought them together into a unified theory. What he discovered was breathtaking. With 4 equations, graceful, compact, and powerful, he described how electric and magnetic fields move, how they generate each other, and how they can propagate through space as waves. In the mathematics, something extraordinary appeared. When electric and magnetic fields oscillate at right angles to one another, they don't just wiggle endlessly, they move, they travel, they form a wave that needs no medium, and that wave moves at a very specific speed. When Maxwell plugged in the known values for the electric constant and the magnetic constant, 2 properties of empty space, he found something startling. The resulting speed was about 299,792,458 meters per second. In other words, the very structure of electromagnetism, buried in the fabric of space itself, predicted a wave that moved at the exact speed of light. And this wasn't some odd coincidence. It was a revelation. Light, Maxwell realized, wasn't just something that came from the sun or glowed from fire. It was an electromagnetic wave, a ripple in the very fields that pervade space. And the speed at which that ripple moved wasn't determined by the sun or fire or any material thing. It was dictated by the deep, unchanging properties of the vacuum. The speed of light was not just a curious fact, it was a necessity. This is the first layer of the answer. Light moves at the speed it does because it must. If you believe in electric fields and magnetic fields, and we have overwhelming evidence that they exist, then you must accept the speed they give rise to. And that speed, by the laws of physics, is not optional. It's woven into the behavior of the fields themselves. If you had a universe with different values for those constants, you would have a different speed. But in our universe, with our space, with our laws, this is the number we get. The speed of light isn't chosen by light. It's chosen by the structure of reality. But there's a deeper layer still, one that goes beyond light itself. Because once Maxwell gave the world this constant speed, Einstein looked at it and asked, what if this isn't just about light? What if this speed is more than a property of waves? What if it's a boundary, a universal limit that applies to everything, not just light, but to space and time as well? Einstein's special theory of relativity turned that idea into a principle. One of the postulates of the theory is that the speed of light in a vacuum is the same for all observers, no matter how fast they are moving. That sounds simple, almost boring, but it changes everything. In ordinary life, speeds are relative. If you throw a ball on a moving train, its speed depends on both your throw and the train's motion. But light doesn't care. Shine a flashlight on a train moving near light speed, and someone standing still will still measure the beam of light moving at exactly the same speed as the person on the train does. No matter how fast you move toward or away from a beam of light, its speed remains unchanged. To make that possible, something has to give. And what gives is the very foundation of how we experience the world. Time slows down, lengths contract, mass increases, simultaneity breaks. Reality itself reshapes around the rule. That's the price the universe pays to protect the speed of light. It's not that light is stubborn. It's that the universe bends to ensure that its speed remains sacred. And if you were to chase light, really chase it, inching closer and closer to its speed, you would discover that every step forward becomes harder than the last. Your mass would increase, not because you're growing heavier in the ordinary sense, but because the energy required to keep accelerating would start to work against you. To reach the speed of light would require infinite energy. And in physics, infinite energy is a polite way of saying, that's not going to happen. It's not just impractical, it's impossible. This is why nothing with mass, not you, not a spaceship, not a grain of dust, can ever move at the speed of light. Because as you approach that speed, the universe begins to push back. It stretches time, it flattens space, it twists cause and effect to keep the balance intact. And the closer you get, the harder it gets, until eventually progress stops altogether. The speed of light stands before you like a horizon, visible but unreachable. So light doesn't go at this speed because it's lucky or powerful. It goes at this speed because it has no mass, and because the electromagnetic fields that generate it have only one way to ripple through space. That one way comes with a fixed velocity. It's not a limit light is trying to reach. It's a definition of what light is. And for everything else in the universe, that speed becomes a ceiling, an asymptote, a line that cannot be crossed. It is not a suggestion. It is not negotiable. It is the rhythm of the universe. And that rhythm governs more than just motion. It governs causality itself. The idea that causes must precede effects, that information must travel through time in the right direction, that signals cannot leap from one place to another without crossing the space between. Without a speed limit, the sequence of events could unravel. You could send a message before you typed it, see an explosion before it happened, rewrite the past by tinkering with the present. But the speed of light keeps time in line. It keeps consequences chained to causes. It enforces a kind of cosmic order. This is why the speed of light matters, not just because it's fast, not just because it's beautiful, but because it is the boundary between what can happen and what cannot. It is the edge of the possible, the scaffolding upon which all physics is built. And light in its tireless motion traces that edge for us. It's the universe's way of saying, here is the speed at which things unfold. Not slower, not faster, just this, always this. And everything else, space, time, motion, memory, takes shape around that quiet, unshakable law. If you could somehow climb aboard a beam of light, riding it like a silent glowing arrow across the cosmos, what would you see? What would you feel? The answer, oddly enough, is nothing. No passage of time, no distance traveled. From the perspective of light itself, if such a perspective could exist, there's no journey, no in-between. The moment a photon is created, whether in the fire of a distant star or the warmth of your fingertips, it is already at its destination, already there, already absorbed. To us, it may have traveled for years, centuries, even billions of years across empty space. But for the photon, no time has passed. It has no clock ticking inside. No before, no after. Just origin and end, stitched together in an instant. This isn't poetic exaggeration. It's a real consequence of Einstein's theory of relativity. As you move faster, time slows down for you relative to someone standing still. That's not metaphor, it's measurable. It happens to satellites, to particles in accelerators, to clocks on jets. But as you approach the speed of light, this slowing becomes extreme. For something with mass, it can never reach light speed because the time it experiences keeps stretching, thinning until it would take infinite energy just to move one bit faster. But light, which is massless, isn't bound by that limit. It doesn't approach the speed of light. It simply is the speed of light. And so, it does not experience time at all. To a photon, every destination is here, and every moment is now. It travels not through time, but outside of it. And that tells us something astonishing about the nature of reality. The speed of light is not just about movement, it's about time itself. It defines the structure of time. It decides how fast or how slow time flows, depending on how fast something moves. It governs simultaneity, which is the idea of two events happening at the same time. And in relativity, that idea, two things happening at once, becomes fuzzy. If you're moving very fast, what looks simultaneous to you might not be to someone standing still. Flash two lights at the same time in your lab, and they might blink out of sync to an astronaut speeding by. The faster you move, the more time and space twist to protect the constancy of light speed. But this twist comes with effects so strange and profound, they sound like science fiction, except they're real. Time dilation, for instance, is one of them. As you approach light speed, time slows down for you relative to the rest of the universe. This is not just a theoretical idea. It's been tested countless times. Particles called muons, created high in Earth's atmosphere by cosmic rays, decay in microseconds when still. But those same particles, when moving close to the speed of light, live much longer, long enough to reach the ground before disappearing. Their internal clocks slow down. They are living proof that time does not tick at a fixed pace. It stretches and contracts depending on motion. So if you were on a spaceship accelerating to near light speed, you could travel across the galaxy in what felt like a few years to you, only to return and find that centuries had passed on Earth. You would have skipped ahead in time, not by magic, but by motion. Then there's length contraction, another consequence of near light speed travel. As your velocity increases, distances in the direction of your motion shrink. You don't notice it from your own point of view. Everything inside your spaceship feels normal. But to an outside observer, your ship would look squashed, compressed along its path. And from your perspective, the universe ahead of you is compressed too. The vast distances between stars collapse slightly, making your journey shorter, even though nothing physically changed in the stars themselves. The universe bends to accommodate your speed, preserving the unbreakable rule that no information, no mass, can ever outrun light. These effects only become noticeable at incredible speeds, fractions of a percent away from the speed of light. But they are always there, always quietly shaping the world. At slow speeds, they're imperceptible. At high speeds, they define everything. And they emerge from a single idea, that light's speed must remain constant for all observers. It's a rule the universe will not break, even if it has to bend time, space, and logic to keep it intact. This principle also underpins the famous equation E equals mc squared, where energy and mass are two sides of the same coin, linked by the square of the speed of light. That number, the speed of light squared, is enormous. It tells us that a small amount of mass contains an unimaginable amount of energy, and that energy, too, obeys the same cosmic speed limit. Nothing, not even energy itself, can move faster than light in a vacuum. The very way we understand motion, power, and transformation is shaped by this boundary. But the most startling consequence of all is the idea of causality. The speed of light isn't just about how fast something moves, it's about what can happen and when. It creates a framework in which cause must come before effect. If something happens far away, it takes time for its influence to reach you. That delay ensures that the past stays in the past and that the future can't arrive ahead of schedule. Without the speed of light acting as a kind of universal brake, that order could unravel. Events could happen in reverse. Messages could arrive before they're sent. Time itself could become scrambled. The speed of light, then, is not just a cap on motion, it's a law that holds reality together. It keeps the universe logical, consistent, traceable. It gives time its arrow. It separates what is from what could be, and what could be from what never was. In every instant, light draws the boundary between the now and the not yet. Every photon that reaches your eye is obeying that law. Every signal you send, every image you see, every word you hear from across a room or across a galaxy, they all arrive on time, never early, never late, always dictated by that one universal pace. And so, when we ask why light can't go faster, we're really asking why reality has structure at all, why time flows one way, why we remember the past and not the future, why events unfold instead of crashing into one another in chaos. The answer, quietly and elegantly, lies in the speed of light. It's not a speed like any other. It's the scaffolding of the universe, the pace that gives everything else meaning, a limit that holds the infinite together. If you could wave your hand and erase the speed limit of light, if you could lift that invisible barrier that holds it to 299,792,458 meters per second, what would happen? It's a tempting idea, almost intoxicating. What if light could go faster? What if messages could leap across galaxies in an instant? What if you could travel to the other side of the universe before finishing a breath? On the surface, it feels like unlocking a superpower, freeing the cosmos from the one rule that slows it all down. But the moment you begin to tug at that thread, reality itself starts to unravel. Because the speed of light isn't just a number, it's the mechanism that keeps time flowing in one direction, that holds cause and effect in order, that binds the present to the future and keeps the past safely behind us. If you remove that speed limit, you don't just make things faster, you make things unstable. You break the story of time. Causality is the principle that cause must come before effect. Strike a match, then see the flame. Push a door, then watch it swing open. It's so deeply embedded in our experience of the world that we rarely think about it. It just feels right, natural, inescapable. But this sense of order, this directional flow of time, isn't just a philosophical assumption. It's a physical consequence of light's finite speed. Because it takes time for information to travel, If someone switches on a light across the room, it doesn't instantly reach your eyes. It gets there quickly, yes, but not instantly. And that tiny delay, that minuscule but measurable lag, is what keeps the sequence of events properly aligned. If you could move information faster than light, if you could receive a message before it was sent, then causality would break down. Effects could precede causes. You could hear the echo before the sound, witness the consequence before the choice. That's not just confusing, it's paradoxical. In fact, this idea has been explored in countless thought experiments. Imagine a device that could send a signal faster than light. You could, in theory, use it to send a message to your past self. Tell yourself to avoid a mistake, to say something different, to make a different decision. But if you changed that event, you would have no reason to send the message in the first place. And if the message was never sent, the event would unfold as it did, and you would be compelled to send the message again. A loop, a contradiction, a paradox that has no resolution. These aren't just philosophical games, they are real consequences of breaking light's speed limit. They lead to contradictions in physics, logic, and the very nature of time. It's as if the universe, in its wisdom, has set this limit as a safeguard, a speed fence to keep time from doubling back on itself. And it doesn't stop at messages. The entire structure of what's called a light cone in space-time depends on light's speed being finite and fixed. At any given moment in time, your position in space defines a cone-shaped region. Everything inside that cone is what can influence you or be influenced by you, given how far light can travel in the time available. The rest of the universe, everything outside that cone, is effectively cut off. No signal, no interaction, no cause and effect relationship can reach you or be reached by you in that moment. The light cone draws a boundary between the possible and the impossible. It tells us what is connected, what is isolated, and how information flows. If light had no limit, the cone would collapse. Everything would be connected to everything else instantly. And that sounds exciting, until you realize that it would erase the structure of time. Everything could happen all at once, or worse, out of sequence. And yet, even within our current universe, we see places where this boundary creates fascinating effects. Look up at the night sky. Every star you see is a story delayed by light's travel time. Some of those stars may no longer exist. Their light left them long ago and only now arrives at your eyes. The further you look, the deeper into the past you see. Galaxies billions of light years away appear as they were when Earth was still cooling from its fiery birth. This delay, this gap between emission and reception, gives us the universe's greatest gift, a window into history. Without it, we would never know what came before. Without the speed of light acting as a bottleneck, we wouldn't be able to see the past. We would be blinded by the now. The finite speed doesn't hinder our vision of the cosmos. It creates it. Astronomers use this delay to do what is essentially time travel. When they observe distant galaxies, they're not just seeing faraway places, they're seeing old light. Ancient photons that began their journey long before our solar system formed. This isn't a poetic analogy, it's literal. That light has been moving, uninterrupted, for billions of years. If it could have traveled faster, we might already have received its story. But then the sequence would be broken, the rhythm disrupted. Instead, the slowness of light, relative to the size of the universe, grants us perspective. It lets us piece together how things changed, evolved, exploded, merged. The cosmic delay is what lets us know that we had a beginning. And it's not just the past that benefits. The present depends on this limit too. Consider space exploration. When scientists send commands to rovers on Mars, the signals, made of electromagnetic waves, can take between 4 and 20 minutes to arrive, depending on the positions of the planets. That delay means the rover must be able to think for itself, at least a little. It must navigate, respond, and act autonomously, because Earth's instructions are never instant. This isn't a design flaw, it's a reality. The universe insists on patience, and our technology has had to evolve to respect that law. Even daily life on Earth is subtly shaped by this limit. Every time you make a phone call or video chat with someone across the globe, there's a tiny delay, not just from technology, but from the fact that light, traveling through fiber optic cables, still takes time. It's small, usually imperceptible, but it's there. Light speed, even at hundreds of thousands of kilometers per second, is not infinite. And the world adjusts accordingly. Timing systems, financial markets, GPS signals, all of them are carefully synchronized to account for the delays that light speed introduces. Without that predictability, systems would collapse. Our web of communication would tangle into confusion. This is the hidden genius of a finite speed limit. It slows things down just enough to allow for order, predictability, sequence. Without it, not only would logic fall apart, but coordination would be impossible. Imagine trying to control a system where everything everywhere happens all at once, where the feedback arrives before the input, where prediction becomes meaningless. A universe without a light speed limit is not a faster, better version of ours. It's chaos. It's noise without pattern, action without outcome, consequence without cause. So while it may be tempting to wish for faster than light travel, to dream of skipping across space in the blink of an eye, we should also be thankful for the quiet strength of this constraint. It keeps the clock ticking. It keeps memories in the past and possibilities in the future. It gives time its direction and stories their shape. It turns existence into a narrative rather than a blur. The speed of light is not just a limit. It is the frame around the picture, the boundary that makes the scene visible, the breath that gives structure to the music of the cosmos. And perhaps, in its unbreakable pace, it whispers a deeper truth, that it's not how fast you move through the universe that matters, but how clearly the universe moves through you. The more we learn about light, the way it moves, the speed it obeys, the laws it follows, the more we begin to see that it's not simply a player in the universe's story. It's the structure on which the story is written. It's the stage and the script and the timing all at once. Light is not just what lets us see the cosmos. It's what defines how the cosmos behaves. And as strange as it may sound, that same cosmic rhythm that guides photons across interstellar distances is the same rhythm that pulses through the objects and technology we use every day. We are not just spectators of the speed of light. We live inside its rules. We build around them. We rely on them, often without realizing it. Every time you open an app, send a message, make a phone call, or look something up online, you're interacting with light. Not the warm yellow glow of a bulb or the dazzling shimmer of sunlight, but electromagnetic pulses traveling through fiber optic cables buried deep beneath cities and oceans, bouncing along glass threads at speeds approaching the cosmic maximum. Each packet of information you send, whether it's a photo, a song, or a single character in a text, travels as flashes of light. These pulses reflect, refract, and weave their way through cables thinner than a strand of hair, crossing continents in the blink of an eye. But even that blink takes longer than the light itself. And yet, fast as it is, that light is still bound by the same ancient rule. It cannot exceed the universal limit. It is always just shy of infinite, always playing by the same number. This matters more than most people ever realize. Global systems rely on it. The timing of stock trades, the synchronization of computer networks, the precise ticking of atomic clocks. Every GPS device, for instance, depends entirely on the speed of light. To find your location, your phone listens to signals from at least 4 satellites orbiting Earth. Each satellite tells the device how long ago it sent its signal. By comparing these time-stamped messages and knowing exactly how far light travels in that time, your phone triangulates your position. But here's the twist. To get it right, GPS systems must account for both special and general relativity. The satellites are moving fast, so time for them runs slightly slower than on Earth's surface. At the same time, they're higher up in a weaker gravitational field, so time runs slightly faster. The combination of these effects would cause huge errors in GPS positioning if we didn't correct for them. But because we understand how light speed governs time, and how that speed remains fixed across all frames of reference, we can compensate with exquisite accuracy. Without the constancy of light speed, our entire global navigation system would fall apart. And that's just one example. The rhythm of light underpins medicine, photography, communication, even the way we cook our food. Microwaves, those long, slow-frequency cousins of visible light, bounce around in your kitchen appliance, heating water molecules and transforming leftovers into dinner. X-rays, on the other end of the spectrum, pass through your soft tissues but get absorbed by bones, creating ghostly outlines that help doctors see what's hidden inside. Lasers, which use the controlled emission of light, power everything from barcode scanners to eye surgeries. Every one of these technologies exists because we have learned not only how light behaves, but how reliably it behaves. Even your own body is a partner in this dance. Vision itself is a product of photons striking the retina, triggering electrical signals that the brain interprets as images. The colors you see are determined by the frequency of the light waves. Blue is a faster wave, red a slower one, but both travel at the same speed through space. That light, reflected off everything around you, carries with it not just brightness, but texture, depth, distance. And as it enters your eye, it becomes something more than information. It becomes experience. Your sense of presence in the world, of knowing where things are, how far away they stand, how they move. All of that is filtered through the limits of light. Your reality is shaped by how fast those photons can reach you. But it doesn't end with the personal. The speed of light also gives us our understanding of the distant universe. Astronomers don't just use light to see, they use it to listen. By studying the light from stars and galaxies, we learn their composition, their motion, their age. A small shift in the wavelength, a redshift or blue shift, tells us whether they're moving away or coming closer. And because light takes time to reach us, we're always looking backward. The further out we gaze, the older the light becomes. Some of the photons arriving at our telescopes tonight left their home galaxies before Earth was even born. That delay, that patient crawl of light across unimaginable distances, gives us our only window into the past. Without it, we would see only the surface of things. With it, we see history written in starlight. And so we come back to that quiet truth. The speed of light isn't an arbitrary value, a number chosen by some cosmic dice roll. It is the tempo that gives the universe its beat. It defines the limits of communication, the edges of possibility, the shape of time itself. It creates separation between what is and what will be, but also connection by carrying the message from one moment to the next. Without that boundary, time would become a blur, events would lose their order, and information could jump around like static in a broken radio. Instead, the speed of light keeps the signal clean. It gives the universe structure, integrity, meaning. And yet, for all its power, for all its foundational presence, light does not demand attention. It arrives quietly, travels without rest, and vanishes the moment its task is done. It doesn't push or pull. It simply moves, always at the same pace, always within the same rules. And in doing so, it becomes one of the few truly universal constants we have, a thread of certainty in an ever-expanding, ever-changing cosmos. So next time you switch on a light, or stare into the sky, or check your map to find the nearest cafe, remember what's really happening. You're not just seeing brightness, you're not just sending data, you're participating in the deep physics of the universe. A universe that flows and functions and remembers its place because of one silent, tireless speed. That number is not just etched in the equations of physics. It is written into the rhythm of life. It is the heartbeat of time, and though you cannot touch it or slow it down, you live within it every second of every day. Light doesn't just show us the world, it defines the way the world shows itself, and it does so always at the same perfect pace.